Assalamualaikum and morning. The next thing that von Karman did uh, after coming up with the quadratic velocity profile in his momentum integral technique was he went ahead and evaluated the boundary layer's thickness, and he used the relations that he got out of the control volume analysis for both the wall frictions as well as the drag on the plate. And so now we combine these together and enable to get the boundary layer thickness. Now we are going to look. Right. So the one common show the relationship of for the momentum thickness delta and is a quadratic velocity profile. So as shown here, the velocity the delta equal to the quadratic velocity profile that we define. So from these equations, if we substitute this into the momentum integral equations, so then we got this, and then we refer this equation as equation number 3. And then he also had a relationship with a wall shear stress. If you look at here, and then we have a wall shear stress. From that, he could obtain uh, and and for the wall shear stress and would have been used the velocity profile that he obtained. So use the same velocity profile here, and then we obtain, and then I put this as a number 4, this equation, so which is a relation with the wall shear stress and the velocity profile. Also from the control volume analysis and uh, and the following, so using the expression from the number 3 and this equations number 4, and then we combine these two equations and we come out with the new equation, which is we call it the equations number 5. Now what we did now is these expressions for the shear stress, and we log back here he had the expression for the shear stress. So we have this as a equation, and then we also have, I put this first as equation number 6, and then we have a equation for the shear stress. When we compare this, we have we modified the equations number 3, we got the number 6, and then now in this equation, if you look at here, these equations also have d theta dx. Then what we did now, we substitute this relation put into these equations, then we get a new wall shear stress equations, which is I put as a number 7 here. So tau wall equal to rho u naught squared d 2 over 15 d theta dx. So from 7 and 4, so the 4 also we know that the tau wall equal to 2 mu u uh, u naught delta. So we have this one. So from this one, we combine with the current that we got in the number 7. So the combinations give us these equations, and then 2 mu u naught delta equal to rho u naught squared 2 over 15 d delta dx. So we can simplify this, and we know that mu over rho equal to the nu, which is a kinematic viscosity, and then this is we equate this, and then we got the delta u naught over 15 d delta dx. So the delta equal to, if you simplify this one, d delta equal to 15 nu u naught dx. So now we integrate these equations. We integrate these equations, then the equations that we use now in this integration. So we integrate these equations with respect to the, okay, and then we put the boundary on it, and these equations we integrate this, and also this one, and then we put the we give them the boundary conditions in order to solve the constants. So we have a half d delta squared equal to 15 nu u naught x plus c1. So apply these this boundary condition into these equations, then we can solve for the c1, and then we got the c1 equal to 0. So then we solve against these equations, then we got the delta squared over x squared equal to 30 nu over u naught x. So then we have this the final d over delta equal to the, what we can see here, this is equal to 5.5 multiplied by square root of nu over u naught x, or we can written this as a 5.5x over Reynolds number, square root of the Reynolds number. So this is the uh, boundary condition, the boundary layer thickness. Okay, remember that we written the boundary of Reynolds number in the boundary layer raised the power of half. This is the power of half, and another way writing the expression of Pengkaman of obtain the thickness and of the boundary layer. And this is a very powerful advancement and had occurred in the fluid mechanics. We derive this. However, I should make the clear that there is a subject to assumes that the velocity profile and quadratic profile, and consequently this is not the perfect solutions, but it was one to help us to quite a bit, and it was actually the pretty close to the actual boundary layers thickness grow for the laminar layer. So what we're going to do in the next segment, or in the next lecture, is we are going to take a look at the skin friction. This is another thing that von Karman was able to calculate using his momentum integral equation.